For centuries, humanity has gazed up at the stars, wondering about the vastness of the cosmos. But there is another universe, equally vast and mysterious, that lies right here, all around us. It is the universe of the incredibly small. Everything you see, the chair you are sitting on, the air you breathe, even your own body, is made of tiny building blocks called atoms. These atoms are the fundamental pieces of matter, the letters in the alphabet of reality. For most of human history, they were purely an idea, a concept dreamed up by ancient thinkers. No one had ever seen one. The desire to finally witness these fundamental components of our world became one of the greatest quests in science. Imagine trying to read a book, but you can only see the paragraphs, not the individual letters. You would understand the general story but miss the details that give it meaning. That is what science was like before we could see atoms. We knew they existed, and we had powerful theories that described how they behaved. But to truly understand how matter works, how chemicals react, and how life itself is constructed, we needed to see them directly. This wasn't just about satisfying curiosity, it was about unlocking a new level of understanding, one that could allow us to build and create things with unprecedented precision, right from the atomic level upwards. The challenge was immense. Atoms are astonishingly small. A single human hair is about 500,000 carbon atoms wide. To see something so tiny required a leap of imagination, a complete rethinking of what a microscope could be. The journey to see an atom was not just a technical challenge, it was a philosophical one. It meant pushing the boundaries of what we thought was possible to observe. It was a testament to our relentless drive to explore, to turn the abstract concepts of our minds into concrete images that we could all look at in wonder. This quest would ultimately lead to one of the most profound breakthroughs in our exploration of nature. So, how do you see something that is smaller than the very thing you used to see? For centuries, our window into the microscopic world was the optical microscope. These instruments use lenses to bend and focus light, revealing tiny creatures in a drop of water or the intricate cells of a plant. But light itself has a fundamental limit. Light travels in waves, and you simply cannot use a wave to see something that is smaller than its own wavelength. It's like trying to measure the thickness of a single hair with a meter stick. The tool is just too clumsy for the task. The wavelength of visible light is thousands of times larger than a single atom, making it impossible for a traditional microscope to ever resolve one. The atom was destined to remain forever invisible, hidden in the glare. To see an atom, scientists needed a new kind of eye. They needed to abandon light altogether and find a new way to feel the world at the atomic scale. This revolutionary idea gave birth to a new family of microscopes in the 1980s. One of the first was the Scanning Tunneling Microscope, or STM. This incredible device doesn't use lenses or light. Instead, it uses a fantastically sharp metal tip, a probe that narrows down to just a single atom at its point. This tip is brought incredibly close to the surface of the material being studied, so close that a strange quantum effect takes place. This effect is called quantum tunneling. Quantum tunneling is one of those wonderfully strange ideas from the world of quantum mechanics. In our everyday world, if you don't have enough energy to climb over a wall, you can't get to the other side. But for tiny particles like electrons, the rules are different. If the STM tip is close enough to a surface, electrons can tunnel across the empty gap between the tip and the atoms on the surface. This creates a tiny electrical current. By measuring this current as the tip scans across the surface, a computer can build a map of the atomic landscape, creating a stunning image of the individual atoms arranged below. Soon after, another brilliant invention arrived, the Atomic Force Microscope, or AFM. This microscope also uses an ultra-fine tip, but it works in a slightly different way. Instead of measuring an electrical current, it measures the tiny forces of attraction and repulsion between the tip and the atoms on a surface. The tip is attached to a flexible cantilever like a tiny diving board. As the tip moves over the bumps and valleys of the atomic terrain, the forces cause the cantilever to bend up and down. A laser is bounced off the cantilever to measure these minuscule movements with incredible precision, allowing a computer to draw a three-dimensional map of the surface, atom by atom. These inventions were monumental. For the first time, we had tools that could bypass the limits of light. They allowed us to feel our way across the atomic world, much like a blind person reading Braille. These microscopes were our fingertips, reaching out to touch the very fabric of reality. Teams of scientists around the world, particularly at places like the IBM Research Laboratory in Zurich, were at the forefront of this revolution. They weren't just building new instruments, they were opening up a new frontier for all of science, preparing the stage for a discovery that would capture the imagination of the world. With these powerful new eyes, the scientific community began to explore the atomic realm in breathtaking detail. We could see the neat, orderly rows of atoms and crystals and the complex arrangements of atoms in different materials. But one challenge remained. To truly test the limits of this technology, scientists wanted to see the smallest, simplest, and most fundamental atom of all, hydrogen. Hydrogen consists of just a single proton and a single electron. Seeing it would be the ultimate demonstration of our newfound power to observe the building blocks of the universe. It was the atomic equivalent of finding the single grain of sand from which all beaches are made. The breakthrough came from a team of brilliant researchers at IBM, including scientists like Gerhard Meyer and Leo Gross. They used a specially adapted atomic force microscope, operating in extreme conditions of ultra-high vacuum and frigidly low temperatures just a few degrees above absolute zero. These conditions were essential to keep the atoms perfectly still, preventing them from jiggling around due to heat. They painstakingly prepared their experiment, placing a single complex molecule on a surface. This molecule acted as a tiny, stable stage. Within this molecule was the prize they were seeking, a network of hydrogen atoms. With immense care, they brought the AFM tip close to the molecule. The tip itself was specially prepared, ending with a single carbon monoxide molecule. This acted as a microscopic magnifying glass, enhancing the tiny forces they were trying to measure. As the tip scanned across the molecule, it traced the faint, ghostly presence of the electron cloud that surrounds the hydrogen atom. The data fed back into the computer and slowly, an image began to form. There it was. Not a sharp solid ball, but a fuzzy cloud-like shape, the quantum mechanical reality of what an atom truly is. They had seen a hydrogen atom. This achievement was incredible. It was like looking at the first photograph of a newly discovered planet. At the same time, another team at Cornell University, led by David Muller, was pushing the boundaries in a different way. They developed an even more powerful electron microscope technique called ptychography. This method uses a clever computational approach to unscramble the information from electrons that have passed through a sample. With it, they were able to achieve a resolution so fine that they could see the jiggle of a single atom due to thermal vibrations. Together, these achievements gave us our first clear portraits of the universe's smallest and most abundant element. Seeing a single hydrogen atom was more than just a beautiful scientific moment, it was a gateway. Once you can see the fundamental building blocks of matter, you can start to think about rearranging them. This capability has thrown open the doors to countless new fields of science and technology. In chemistry, for example, we are no longer limited to guessing how molecules fit together. We can now directly image them, watching how chemical bonds form and break during a reaction. This gives us an unprecedented understanding of the processes that drive everything from the creation of new medicines to the development of better batteries. The impact on technology has been just as profound. The ability to see and manipulate individual atoms is the very foundation of nanotechnology. This is the science of building things on the scale of atoms and molecules. Imagine tiny machines smaller than a blood cell that could be sent into the body to target and destroy cancer cells. Or materials that are programmed at the atomic level to be incredibly strong, lightweight, or self-repairing. These ideas, once the stuff of science fiction, are now becoming a reality because we have the tools to work at this unbelievably small scale. The future of manufacturing may not be in giant factories, but in tiny labs where we build our world atom by atom. This breakthrough has also propelled us toward the next great computing revolution, quantum computing. A quantum computer stores and processes information using the quantum states of individual atoms or particles. To build such a computer, you need to be able to control these atoms with absolute precision. The imaging techniques developed to see the hydrogen atom are essential for building and testing these new quantum devices. By observing how these quantum bits or qubits behave, we can learn how to harness the strange power of the quantum world to solve problems that are impossible for even the most powerful supercomputers today. In the end, the story of seeing the hydrogen atom is a beautiful story about human curiosity. It shows that when we are driven by a desire to understand the universe, we can achieve extraordinary things. We learned to see something that was thought to be forever unseeable. We built eyes that could look beyond light itself. And in doing so, we didn't just see the smallest thing in the universe. We opened up a whole new cosmos of possibilities. The simple act of looking at something so small has changed our world forever, reminding us that the greatest wonders are often found not just in the distant stars, but in the tiny, intricate details of the world right under our noses.